We'll be discussing Lab 2, lines of charge. This lab was pretty much a continuation of Lab 1, in which we charged up 2 tapes and used computational models to determine the charge on the charge tapes. So in Lab 1 we used a point charge model to represent the charge tapes, and now in this lab we will be using a point charge, or a line of charge model, in which the tape actually has some length to it. So this divides our tape into multiple point charges that are spaced evenly, and the hope here is to more accurately model the system. The results from Lab 1 point charge model, the tape charge was found to be 4.6 times 10 to the minus 10 coulomb, and in our line charge model it was found to be 4.6 times 10 to the minus 9 coulomb, so an order of magnitude difference. So the fundamental principles here are the same as Lab 1. Okay, we're using the Newton's third law, where the force of A on B is negative the force of B on A. Coulomb's law describes the force between two charged objects. And the law of universal gravitation here describes how objects are attracted towards one another gravitationally. So here are some details of the experimental system. This was how we charged the tapes experimentally, laid down one tape, added another tape, and ripped them off to produce the charged tape. Here are some numbers. And in order to determine the charge on the tape, we used this apparatus here, in which we suspended one charged tape between two stands, and then held the tape underneath it. The displacement of tape B was used to compute the charge on tape A. The surroundings here include everything that, everything that's not the two tapes is the surroundings. So here are some calculations from Lab 1, again exactly the same as Lab 1. Here's how we found the charge on the tape and the number of electrons lost on the tape. And for Lab 2, we used this equation, which is the electric charge of a finite rod. Okay, I got this from this source here. So in order for the top tape to be displaced here, tape B to be displaced, the magnitude of the electric force must overcome the force of gravity, which has this value here in newtons. So we computed, this was the force of gravity here, which must be equal to the force of the finite rod, in other words, our lower tape. And this is how we solve for Q here. Okay, so Q comes out to 4.6 times 10 to the minus 9 coulomb. So now let's discuss our computational model here. Here are the numbers we used in this model. These are constants. This was the mass of our tape, and this was the estimated charge on tape that comes from the point charge model. Okay, next up we used the same E-field function as last time, and this line charge function creates a line of charge. Okay, this code here adds up each modeled point charge from the lower tape on the top tape. So essentially we split up the lower tape into a bunch of small point charges, add up their E-field vectors in this for loop, and then this creates the net electric field at the top charge due to the entire bottom tape. So here are the results from this code. The green arrows here represent the E-field from each DQ, so as you will see, they add up and they start to diverge separately because over here these E-field vectors coming from over here are now at an angle. The white is the force vector of the blue tape on the red tape, and the yellow is the force vector of gravity on the red tape. And it makes sense that these would be equal. And as we see here, the electric force and gravitational force come out to just about the same within some error. So there were some assumptions that we made in this model, which were the same as Lab 1. Okay, firstly, we assume that air resistance is negligible and friction. In Lab 1, of course, we modeled the tape as a point charge, which we know isn't physically accurate. And we also assumed that each tape had charge evenly distributed along the entire length of the tape. Okay, and this leads to some errors where, obviously tape is not a point charge. That's the whole reason we did this line charge model. Obviously, tape is very heavily subject to air resistance, and we have to handle the tape in order to perform our experiment, which causes some loss of charge, and the charge very easily bleeds off upon touching anything. So here's our discussion. So what's the difference between modeling the tape as a point charge versus the line charge? Lab 1, of course, used the point charge assumption and gave a charge that was an order of magnitude less than Lab 2, which uses the line charge model. And why are these different, and which one is more accurate? Well, again, they're different because the line charge model accounts for the tape's length, which also makes it more accurate because in our real world that we did the experiment, the tape did have a length of 0.2 meters, and so it cannot be accurately modeled as a point charge.